Well, hi everyone, this is Bob the Science Guy. Today we're going to talk about something that's near and dear to everybody's heart, money. Specifically, we're going to talk about something called compound interest, which is the interest that you pay on car loans or the interest that you get back on annuities or other investments. Now, this also has to do with demographics such as population numbers, the growth of bacteria, and even radiometric dating. So let's dive right into it and learn how to figure out compound interest. Now, many of us are familiar with this number. It's 3.14159. That's our friend pi from high school. There is another number that is equally important, if not more important, and that is this number, 2.71828. And that number is called E, and that stands for Euler's number. Now, why is Euler's number important? Well, it's the key to something called exponential growth. Let's go over an example. Say we have a city of population P, and we know that every 50 years that population doubles. What's the growth rate of the city? What will the population be in 20 years? How long will it take the population to increase 5 times over what it is now? These are very important questions that city planners might ask, especially when they're building a new bridge that's going to last 50 years or 60 years. Will that bridge have enough capacity to handle the anticipated change in population over the life of the bridge? Let's see how to figure out these questions and more on the slide rule. So ideally what we would like is we would like to take a population or the principal of a loan or whatever and multiply it by some magic box and be able to tell what the future is. Well, what goes in this box? If you guessed Euler's number, you'd be right. So the number that goes here is E raised to a power. And what's that power? Well, it's the rate times the time. Now, lots of times you'll see this written as P e to the RT, or PERT. So here we have, this is our population. This is the magic box, and the answer is the future. Well, here's the math behind everything. So, if we have a city population of P, and we want to know the doubling time, how long does that population require to get to 2P? Now we divide both sides by P, and we end up with 2 equals ERT. Now, if you want to get really fancy, you can then take the natural log of both sides, so you get the natural log of 2 equals R times T. So to do this on a slide rule, we need to introduce a couple of new scales, ones that you may not have seen used before, and those are the LL scales, the log-log scales. Let's have a look at our virtual Pickett N3 and see where these scales are and how to use them. Okay, now here's our old friend. This is the virtual Pickett N3. The link to this is in the description. And this is the side that we've normally been using, but for today, we're going to flip it over to the other side by hitting this little box. And there it is. On this, you will see some new scales. You'll see on the left side, you'll see LL0, LL1, and then that's on the upper stator, and on the lower stator, you'll see LL2 and LL3. These are the log-log scales, and they're used to look at exponential functions. For example, if you wanted to know what 2 raised to the power of 3 would be, let's go ahead and see how to do that. Okay, so if we start off on the LL2 scale, you'll notice that there's a black and a red. We want to go with the black because we're dealing with a number greater than 1. Now, if you go just to the left, you will see 2.5 right next to the 9, just to the right of it. And then as we come over a little bit further, you see a 2.0. So what we are going to do is we're going to take the slide and we are going to put it directly over 2.0. Now what we'll do is, without moving the slide, we'll just kind of move the entire rule over a little bit until we see 2 on the C scale. And if we look at 2 on the C scale and put our hairline directly over it and look straight down to the LL3 scale, you'll see that the hairline is at the little black mark that says 4. That's because 2 raised to the power of 2 equals 4. Now if we come out here to the 3 on the C scale, and once again read straight down, we see that there is an 8. Now, not only is this a very convenient way to raise virtually any number to any power, it takes care of the decimal place for us. So when we look at 2 to the 3 and we see an 8, that means 8. It doesn't mean 0.8, it doesn't mean 800, it means 8. So unlike the rest of the slide rule, we don't really need to keep track of our decimal places because it does it for us. Now let's get the slide out of the way so we can see how to solve this population problem. Now, if you happen to notice down on the LL3 scale, in black, the very first entry under the 1 on the D scale is E. That's Euler's number. And if we come out to where the 2 was on the LL2 scale, we see that it's just below and to the left of the 7 on the D scale. That means that 2 is E raised to the power of about 0.69. So here's where we stand. 2 equals E raised to the power of 0.69. Remember, E is greater than 2. It's actually 2.71828. So it makes sense that you would have less than 1 in the exponent here. But what about this 0.69? Where does that come from? That equals the growth rate times the time. Well, we know that the time is 50 years. What's the growth rate? That's actually very easy to figure out. So what we have now is we still have LL2, and you notice that 2 is now right underneath the hairline. And as you can see, that works out to about 6.93 or 4. Well, let's divide that by 50 years. So we'll put the 5 right over that point. Then all we do is we just bring our cursor over and put it on the index of the C. And if we increase this a little bit, we can read off the growth rate. It is 1.389%. So let's go back to our equation here. So this is the natural log of 2, and this is the exponent on E in order to give us 2. Now, we have 50 years, so what we can do here is take 0.69, divide it by 50, and that will equal our population growth rate. And while we can do this on the slide rule, I happen to have my calculator right here, and here is our growth rate. Now, mind you, this is 0.0138. In order to get the percentage, you have to multiply this by 100, and it becomes 1.38%. Now, putting this into a growth rate calculator, I just picked a random number for the initial value of 20,000. Our annual growth rate is 1.38%, and our time is 50 years, and if we hit calculate, what do we get? While this isn't quite a complete doubling, you can easily understand that I've rounded this to just 2 decimal places. If I put a couple more decimal places on that, we'd certainly get a lot closer to 40,000. Now, as you may recall, the slide rule has an interesting feature called a table function, which means that once we set it up once, we don't have to move anything other than the cursor to get a bunch of other answers. Let me show you what I'm talking about. Now, as you recall, the population doubles every 50 years, so on LL2, we have 50 years on the C scale, and then we have 2 on LL2. Well, one of the questions that we had is, okay, well, the bridge is set to last 60 years. What will the population of the city be in 60 years? All we have to do is move it over here to the 6, and then we just read it off directly. This is we've got 2, 2.1, 2.2, just shy of 2.3 times the initial population. And of course, once again, what's the population going to be in 30 years? Well, there it is. And if we zoom that in, and in 30 years, we will see that the population will be 1.515 times the current population. Well, now that we know the basics of how the LL scales work, let's go ahead and review that real quick and start looking at investments and loans. Now, as you recall, when we looked at our population growth, we said that the population doubled every 50 years. So what we did was we looked for 2 on LL2, and then we put 50 years directly above it. And then we came back to the index on the C scale and looked straight down onto D and read off the growth rate, which was 1.39 or so percent per year. Well, we can kind of do the same thing. Say we want to put an investment in at 3% interest. We simply put the index directly over the 3, and then we come back out to where the 2 is on the LL2 scale, and we can see that we will double our money in a little bit over 23 years. What interest rate would we need to have if we wanted to double our money in 20 years? Well, all we have to do is bring the 2 over here, directly over the 2 on the LL2 scale, and then we read back here and we see our interest rate, which is going to be about 3.47%. Now let's say you have a relative pass and they leave you a sum of money, say $100,000, and you have an opportunity to invest that at 6.5% per year. Is that going to be enough to generate $1 million for your retirement in 30 years? Well, that calculation is very simple as well. So what we'll do is we'll come out to the slide rule, we'll take the right index of the C scale and put it directly over 6.5 on the D scale. Then we'll come to 30 years on the C scale and we'll read down onto LL3 and see what we have. We're going to increase our money approximately 7-fold. So your $100,000 will become $700,000, which means that you're going to fall short. And if we run that through our calculator, we see $100,000 at 6.5% over 30 years is going to come out to $661,500. Again, we're dealing with rounding errors here. But the bottom line is, even with a good nest egg of $100,000, you're going to fall a little short of your goal. And the only way to fix that is to add additional money over the next 30 years. But it's still reachable. And the sooner you add the money, the more interest you'll collect because it'll accrue longer. Now, the interesting thing is this doesn't work just for interest rates or rates of growth. It also works for decay rates. Let's look at carbon-14 dating. Now, the way that carbon-14 dating works is that you take the original amount of carbon-14 and then you multiply it by e raised to the negative c t. Notice how similar these are. C is the decay rate, and it's negative because the quantity is getting smaller, whereas R here is the growth rate. T is the same for both. Now, I mentioned earlier that there are numbers that are in red. Now, the LL scales are set up differently on different slide rules, but this one uses a combined scale. So the black numbers are greater than 1, and the red numbers are less than 1. And you see right here, what I've done is I've lined up the hairline with the 0.5 on LL2. Now, when we dealt with interest rates, we looked at doubling rates. But with radioactive decay, we do something called the half-life. And the half-life of carbon-14 is 5,730 years. Now, what's interesting on this particular slide rule is we have a gauge mark or a calibration mark. There's a little r at 57.3 because that is used to convert degrees to radians. It's convenient that 5,730 years is the half-life of carbon-14. So we just line up that gauge with the 0.5 on the red scale on LL2. Now, if we look over here, you will see that the decay rate is about 1.21. Now, that's not 1.21%. It's actually just a couple of orders of magnitude lower because you're dealing with 5,700 years rather than 57 years. But now we have this set up and we can sit down and we can figure out how old a sample is. Now what we can do is we can look down at LL3. For example, right here, that would be 1% of the sample left. That would mean that the sample is approximately 38,000 years old. You can see that on the C scale. Likewise, if there is 5% left, the sample would be approximately 24,800 years old. Continuing on, we can go to 10%, and we get about 19,000 years old. So in this episode, we had a look at population growth, we had a look at continuous compounded interest, and we had a look at radiometric decay. Take your slide rule out, learn to use those LL scales, have a little fun with them. Sit down and maybe look at some possible loans that you could get. You could look at a mortgage. What's the advantage of having a 15, a 20, or a 30-year mortgage? Well, what are the equivalent interest rates that you would look at? And how much would you pay back in interest? All of this can be figured out on a slide rule if you just sit down and play with it a little bit. So, this is Bob the Science Guy. Thank you very much for stopping by. And remember, you too can be awesome on a slide rule. Take care, guys.